Right, good morning. So last week we started discussing the duality theory, basically. So what we did was we had an LP problem to start with. And our goal was to find an upper bound on the optimal value of a maximization problem. And then that gave rise to another LP problem, which we called the dual LP problem. And last time we actually saw how to derive the dual LP problem of any LP problem in any form. So today we're going to continue our discussion. So we're going to start with duality theorems. So essentially we're going to see that there's a very nice relationship between a primal problem and its corresponding dual problem. So this is theorem number 6. So this is known as the weak duality theorem. And I will just use WDT for short. Okay? And here's a statement of the theorem. So consider the primal dual pair of, consider the following. Primal dual pair of LP problems. So here's our primal problem, which I denote by P. So P stands for primal. I want to maximize the linear function, Cx, subject to linear inequality constraints, and also to the constraint that the decision variables be non-negative. So remember, this was the original LP problem that we started with, and then we wanted to drive an upper bound on the optimal value, and that gave rise to the following LP problem, which we call the dual, and I'm going to denote by D. I'm going to minimize WB, subject to WA is at least as large as C, and W is non-negative. So remember, the dual problem actually arises from the fact that we would like to get the best possible upper bound. So the best possible upper bound basically means the smallest upper bound, and that's the objective function of the dual problem. And then the constraints basically ensure that you have to pick the multipliers W so that they satisfy a certain relationship. All right, so here's a statement of the theorem. So let X bar be a feasible solution for the primal problem. And let W bar be a feasible solution for the dual problem. Then we always have the following inequality. So if I look at the objective function value evaluated at the primal feasible solution X bar, then that value, that objective function value, is always less than or equal to W bar times B, which is precisely the objective function value of the dual problem evaluated at the feasible solution W bar. Okay? So in other words, the objective function value of every feasible solution of D, every feasible solution of the dual problem, is at least as large as the objective function value of every feasible solution of the primal problem. So essentially what the weak duality theorem says is the following. So whenever I have a primal dual pair of LP problems, if I pick any feasible solution from the primal problem, and if I pick any feasible solution from the dual problem, and if I evaluate the objective function values, then the primal objective function value is always less than or equal to the dual objective function value. Okay? Now, if you think about how we derive the dual problem, this shouldn't be a surprising result, because the dual problem actually, remember, was trying to give us an upper bound on the optimal value, right, on the primal optimal value. So this basically just formalizes that sort of discussion. So whenever you have primal dual pair of LP problems, if you pick any feasible solutions from each problem, then the primal objective function value is always less than or equal to dual objective function value. In other words, every feasible solution of the dual problem gives you an upper bound on the primal optimal value. Okay? And conversely, every feasible solution of the primal problem actually gives you a lower bound on the dual optimal value. Okay? So we're going to try to prove this result. The proof is pretty simple, actually. So I'm going to try to convince you formally that indeed the objective function value of the primal problem is always less than or equal to the objective function value of the dual problem. Okay? So how do we prove such a result? Well, so let W bar be a feasible solution of D. So by definition of feasibility, for the dual problem, W bar should satisfy all of these requirements, right? So W bar times A, so this implies that W bar times A is greater than or equal to C, and W bar is non-negative. So remember, W bar is actually a row vector, right? So it actually contains m variables for the dual problem. So now what I'm going to do is I'm going to focus on the first inequality. Okay, so W bar times A should be at least as large as C. And I will multiply both sides from the right by the vector x bar. Okay, so since x bar is non-negative, I'm allowed to do that. We have W bar times A times x bar is greater than or equal to C times x bar, where x bar is the primal feasible solution. Okay. So one thing, again, you should be careful about here is that this is actually a vector inequality, okay? And what I'm doing here is that basically I'm taking each vector or each inequality and multiplying it by some non-negative number, and I'm adding them up, basically, okay? So if you think of the inner product, so essentially what I'm doing is I'm taking the inner product of this vector with this vector, and this vector with this vector, basically, right? So this is just a scalar inequality, just a single inequality, okay? Any questions so far? All right. Since x bar is also feasible for the primal problem, so this means that by definition of feasibility, x bar should satisfy all of these conditions at the same time. So this implies that ax bar should be less than or equal to b, and x bar is not negative. Okay? All right, so now let me focus on the first part again. So a times x bar is less than or equal to b, right? So remember, that's again a vector inequality. Ax bar is a column vector, b is a column vector as well. Okay? And note that ax bar also appears over here, right, in this inequality. So then what I'm going to do is, again, since W bar is non-negative, I'm going to multiply both sides by W bar over here, okay? So this implies that W bar times A times X bar will be less than or equal to W bar times B. Okay, I'm just taking the first inequality and multiplying both sides from the left by W bar. Okay, I'm allowed to do that because W bar is non-negative, so that the inequality does not change direction. Okay? All right, well, so now all I need to do is just combine these two inequalities, right? So think of this as my first inequality. This is my second inequality. So W bar AX bar is at least as large as CX bar, but it's no more than W bar B. So if you combine these two inequalities, okay, so what's the resulting inequality? So W bar B cannot be more than C times X bar, basically, right? Okay? So it's the other way around, sorry. C times X bar is less than or equal to this, and this in turn is less than or equal to W bar B. So as a result, C times X bar should be less than or equal to W bar times B. And that's exactly what we're trying to show, okay? So once again, I mean, if you think about how we obtained the dual problem, this shouldn't be a surprising result because the way we obtained the dual problem was it stemmed from the sort of need to find an upper bound on the optimal value of the primal problem, okay? So all this says is that every feasible solution of the dual problem actually gives you an upper bound on the optimal value of the primal problem, okay? So this is just a formal way of stating that result. And of course, since I'm interested in finding the best upper bound, that's why we minimize the dual objective function. So we're trying to find the smallest upper bound, okay? So we're trying to make this upper bound as small as possible, basically, okay? And of course, you can think of it in the other way around. So since the primal and dual are symmetric, if you think of this as your primal problem, then this would be the dual problem. Okay? So now you're trying to find the best lower bound on the optimal value. Okay? So you're trying to maximize this one. So this is a lower bound. So you're trying to make this as large as possible, basically. Okay? So one way to say this is the following. So think of this as a real line. So we have plus infinity and minus infinity. Okay? On the right and on the left. So essentially, the primal problem is trying to maximize c times x. So it's trying to make this value as large as possible. It's trying to push it to the right. And the dual problem is trying to actually make w times b as small as possible. So it's trying to push w times b as far to the left as possible. Okay? So what this result says is the following. So whenever I have any feasible solution for the primal problem, and if I look at the corresponding value, I get something like this. And if I look at any feasible solution for the dual problem, so this value can never go to the right of this value, basically. It can never be larger than that. And conversely, this value can never go to the left of this value. It cannot be smaller than that. Okay? So one way to think about this is you can think of the primal and dual problems. It's like, in a way, they're playing some games. Okay? The primal problem is trying to make this as large as possible, and the dual problem is trying to make this as small as possible. Okay? So that's the perspectives of the two problems in some sense. Does it make sense? All right. Now here comes the following corollary. So if x bar is feasible for the primal problem, and w bar is feasible for the dual problem, and in addition, so we have from theorem 6 that c times x bar is always s equal to w bar times b, right? So this inequality is always true. So suppose that we have equality basically. Suppose that these two values are the same. Then the question is, what can I say about x bar and w bar? So just look at this real line. So suppose that it turns out that these two values actually coincide. Okay? So what does that imply? Or does it imply anything? Exactly. Okay? Then x bar is optimal for the primal problem, and w bar is optimal for the dual problem. Now this is also an important result. What it says is the following. So if these two values happen to coincide, happen to be the same, then the respective solutions should be optimal for the corresponding problem. So x bar should be optimal for the primal problem, and w bar should be optimal for the dual problem. And one way to see this is the following. So suppose that these two actually coincide at this point right here, okay? So suppose that this is my cx bar, which is the same as my w bar b. Okay? And what I want to do is the following. I want to say that I cannot find a better solution than x bar for the primal problem. Okay? Now one way to say this is the following. Well, if you look at this result, you know that c times x bar can never be larger than w bar b, which means that c times x bar can never go beyond this value, right? Okay? Well, since you're trying to minimize c times x, obviously the best you can do is this point right here. So you cannot go beyond that point, okay? And also, if you think of it from the dual perspective, well, you know that w bar b can never go to the left of this value, okay? And you already have a solution that's equal to this value, so that should be the best solution for the dual problem as well. Okay? So I'll just give you a formal proof, but that's essentially the same idea. So let x prime be any feasible solution for the primal problem. And I want to show that x prime cannot be better than x bar in terms of the objective function value. Okay? or I need to show that x bar is at least as good as x prime, basically. Okay? So by the weak duality theorem, by WDT, we know that C times x prime should be less than or equal to W bar times B. So where does this come from? Well, if you look at this result, so since x prime is feasible for the primal problem, and W bar is feasible for the dual problem, we have this inequality, right? I'm just applying this inequality with x prime and W bar, basically. Okay? So once again, all I'm doing is I'm just picking any feasible solution for the primal problem. Okay? And if I look at the objective function value, C times x prime cannot be more than W bar times B. Okay? So I'm just using that inequality over there. Okay? All right. But by my assumption, I know that W bar B is the same as Cx bar. So W bar B is the same as Cx bar. So this implies that C times x prime is less than or equal to C times x bar. So if I simply replace W bar B by C times x bar, then I have this inequality. Well, what does that inequality tell us? The objective function value of any primal feasible solution cannot be larger than the objective function value of x bar for the primal problem, right? And remember, primal is a maximization problem, so that means that this is the best possible solution, right? This is the best possible objective function value. So this inequality shows you that if you give me any other feasible solution, its objective function value cannot be larger than C times x bar, basically. Okay? And since this is a maximization problem, the best you can do is exactly C times x bar. Does it make sense? Okay? So this shows that, so this implies that x bar is optimal for the primal problem. So conversely, I need to show you that W bar is optimal for the dual problem. I'll just reverse the argument now. Okay? So what I'm going to do is, so let W prime now be any feasible solution for the dual problem. And I need to show you that W bar should be at least as good as W prime. Okay? Or W prime cannot be better than W bar. Okay? So again, by the weak duality theorem, I know that W bar times B should be at least as large as C times x bar. I'm just applying the weak duality theorem once more for the dual feasible solution W prime and the primal feasible solution x bar. Okay? So C times x bar is less than or equal to W prime times B, basically. Okay? All right. So I'm going to use this inequality once again. But C times x bar is the same as W bar times B. So this implies that if I plug in or substitute that value, I have this inequality, basically. So the objective function value of any arbitrary feasible solution is at least as large as the objective function value of W bar for the dual problem. Okay? And the dual problem is a minimization problem, so the best I can do is exactly this value right here, so this should be the best solution. Okay? So this implies that W bar is optimal for D. So it's a very simple application of the weak duality theorem. So all it says is that if you happen to have solutions for the primal and dual such that their objective function values are the same, then those solutions should be optimal for each problem, basically. Okay? So in general, you always have this inequality. But if it happens that you have equality here, then the corresponding solution should be optimal. Okay? That's important. Okay? So corollary number 1 just tells you that if the values are the same, then the corresponding solution should be optimal for each problem. Okay? So what it doesn't tell you yet is the following. It doesn't necessarily tell you that they should always be the same. Okay? It just tells you that if they are the same, then they should be optimal. Okay? Any questions about this result or about the theorem? So once again, I mean, it's important to sort of keep this picture in mind. So think of the primal and dual as like playing a game against each other in some sense. Okay? So the primal problem is trying to make Cx as large as possible, and dual problem is trying to make WB as large as possible. And if they happen to meet at the same point, then they should be the best solution. So that's important. Okay? Questions? All right, so let me give you an example. So So suppose that my primal problem is given by the following. I want to maximize 2x1, sorry, x1 plus 2x2. And my constraints are x1 plus x2 is less than or equal to 6, and x2 is less than or equal to 3. And x1 and x2 are non-negative. So this is my primal problem, which is exactly in the same form as the statement of the theorem. So we have ax less than or equal to bx non-negative. It's a maximization problem. Now, what is the corresponding dual problem? So let's work on the dual problem. So apart from the non-negativity constraints, we have two inequalities. Okay, so which means that we're going to need two multipliers, right? So we can call them W1 and W2. What is the objective function of a dual problem? So remember, what you do is you take the inner product of these multipliers with the right-hand side vector, right? So the dual will be a minimization problem, since the prime is a maximization problem. So we're going to minimize 6 times W1 plus 3 times W2. Now, what are the constraints? So I'm going to look at the first column, basically. W1 times 0 W2. So if you look at these statements, we have ax less than or equal to b. Dual is greater than or equal to c, basically. So we should have greater than or equal to. So what's the right-hand side value? The right-hand side value is precisely the objective function value, right? So it's going to be equal to 1. I'm going to look at the second column. So W1 plus W2 is going to be greater than or equal to 2. And then W1 and W2 are non-negative. And hopefully everybody remembers how to take dual, right? So, okay. All right, so in this case, both problems have only two variables, so I can just graph the feasible region. So let me start with the primal problem. x1 plus x2 less than or equal to 6 looks like this constraint. And then x2 less than or equal to 6, sorry, x2 less than or equal to 2, x2 less than or equal to 3 rather. It actually looks like this one, right? And then we have non-negativity, so this is the primal feasible region, basically, right? All right, so similarly, let's draw the feasible region of the dual problem. So this is my W1 and this is my W2. So what does the first constraint look like? W1 is at least 1. So what's the corresponding region? So I'm going to start with W1 equals 1. And I'm going to look at the right-hand side because W1 should be at least as large as this, right? So what about the second constraint? So it goes through 2 and 2. And what's the correct region? So if you plug in the origin does not satisfy that inequality. So as a result, it's the side which does not contain the origin. Okay? And then we have non-negativity of x, W1, W2. So this is the feasible region of the dual problem, basically. Okay? All right, so now what I'm going to do is I'm going to look at, of course, I mean, in general, we have infinitely many feasible solutions, right, in both problems. But we know that we always have a finite number of corner points, right? So both problems have only a finite number of corner points. So how many corner points are there for the primal problem? There are 4 of them, right? So these are the 4 corner points. What about the dual problem? What about dual problem? How many corner points are there? There are only 2, right? So there's this one and this one, basically. Okay? So now what I'm going to do is I'm going to look at the objective function values evaluated at those corner points, okay, for each problem. So let me give them some numbers. So let's call this corner point 1. Okay? So what are the coordinates of corner point 1? They're just 0, 0, basically, right? So what's the corresponding objective function value? So at 1, the objective function value, which I'm going to denote by z, is equal to 0. Okay? let me call this one solution number 2. So what are the coordinates of the second corner point? 6 and 0. So what's the corresponding objective function value? So it's going to be equal to 6. And then let me call this one solution number 3. What are the coordinates of solution number 3? 0 and 3, basically. And if you plug in the objective function, you get 6 again. So which means that corner points 2 and 3 are on the same isopropyl line, basically, right? Okay. And this is solution number 4. What are the coordinates? So if you think about this a little bit, it's basically 3, 3. It's not too hard to see that the coordinates are 3, 3, and the objective function value will be equal to 9, basically, right? So which means that this will be my optimal solution, basically, right? Since this is a maximization problem, this is optimal. All right, so let me call this corner point 5. So now we're looking at the dual problem. So I'm going to look at the objective function of the dual problem, right? Okay. So at 5, the coordinates are given by 2 and 0, right? So what's the corresponding objective function value? So if you plug in 2 and 0 into the objective function, you get 12, basically, right? All right. So let's call this corner point 6. What are the coordinates here? Well, they're actually 1 and 1. Okay. What's the corresponding objective function value? So it's equal to 9. Okay. And since this is a minimization problem, this is the best possible solution. So this will be optimal for the dual problem. Okay. So one thing you should pay attention to is the following. If you look at the objective function values here, okay, they're always less than or equal to objective function values over here. Okay, so this is precisely what the weak duality theorem says. So the values here cannot be larger than the values on the right-hand side. Okay, and secondly, if you look at corollary number 1, so we have a primal solution whose objective function value is 9. We have a dual solution whose objective function value is 9. So that means that by corollary 1, this is optimal for the primal problem, and this one is optimal for the dual problem, basically, right? Okay, so once again, the values here cannot be larger than the values on the right-hand side. Okay, and secondly, we have a pair of solutions in which the values agree, the values are the same, so which implies that this solution should be optimal for the primal problem, and this solution should be optimal for the dual problem, basically. Okay, does that make sense? All right, any questions? So this example just tells you basically, or illustrates how weak duality theorem works, and also illustrates corollary number 1. Okay, so if you happen to have solutions for the primal and dual problem such that the objective function values are the same, then you can stop and say that they should be optimal for the corresponding problems. Okay, and in this particular example, corner point 4 for the primal problem and corner point 6 for the dual problem have the same objective function values, so they should be optimal for the corresponding problems. Okay. Another way of saying this is the following. So in the primal problem, you can never find a solution with an objective function value greater than 9. Because if you could, then you would violate the weak duality theorem, right? Okay? And conversely, for the dual problem, you can never find a solution whose objective function value is smaller than 9. Because if you could, again, you would actually violate the weak duality theorem. Okay? All right. Any questions? Okay. So this was the first relationship between the primal and dual problem. So let's look at some other relationships. Corollary number 2. So if either one of primal or dual problems is unbounded, then the other problem should be infeasible. The other LP problem is infeasible. So first of all, let's try to understand what the statement says. So I give you a pair of primal and dual problems. Suppose that the primal problem is unbounded. Okay, so suppose that this problem is unbounded. Then the claim is that the corresponding dual problem should necessarily be infeasible. Okay, cannot have any feasible solutions. And conversely, if the dual problem is unbounded, then the corresponding primal problem should be infeasible as well. Okay? Now, where does this come from? So why is this true in general? So always keep that real line in mind. So this is my real line. The primal problem is trying to maximize Cx. Okay? And the dual problem is trying to minimize Wb. So this is my primal problem. This is my dual problem, okay? So now what I'm interested in, or what I'm assuming is the following. So the primal problem is unbounded, which means that I can make Cx as large as possible. I can push it as far to the right as possible, okay? And I claim that if I can do that, then the dual problem should be infeasible. The dual problem cannot have a feasible solution. Well, here's the easiest way to think about this, okay? So this is a technique known as proof by contradiction, okay? Suppose that the primal problem is unbounded, okay? But let's say the dual problem is not infeasible, okay? So let's try to see what that means. So suppose that, just to arrive at the contradiction, the primal problem is unbounded, but the dual problem is not infeasible, okay? Well, if the dual problem is not infeasible, that means that it has at least one feasible solution, right? By definition. And whatever that solution is, let's call it W bar, there's a corresponding objective function value, right? So basically, on the real line, somewhere in the real line, there's going to be a corresponding value of W bar B, okay, for the objective function value of the feasible solution of the dual problem, okay? Well, so now if you think about the weak duality theorem, I know that, the primal values can never go beyond this value, basically, right? So this is, or the primal objective function value is blocked by this value, okay? Which means that the primal objective function value can never go to the right of this value. Well, if the primal objective function value cannot go to the right of this value, then the primal problem cannot be unbounded, basically, right? The objective function value cannot be more than this one. But by definition of an unbounded problem, I can make Cx as large as possible, so I get a contradiction, basically. Okay, these two cannot happen at the same time. Does that make sense? Let me give you a formal proof again. So suppose that P is unbounded. Suppose that P is unbounded, but D is not infeasible. Okay? So this implies that then D has a feasible solution. So then D has at least one feasible solution. And let's call it W bar. Okay? So this implies that by weak duality theorem, by WDT, every feasible solution X bar of the primal problem satisfies the following inequality. C times X bar cannot be larger than W bar times B. Okay, so that's the inequality from the weak duality theorem. Yes?
Şimdi burada şu yani iki şey geldi aklıma yani işte bunlar birbirini geçemiyorlar yani şu. O zaman biri unbounded'ken şöyle mi diyoruz yani aralarındaki mesafe sonsuz kadar büyük olduğu için ne kadar yaklaşsalar da sonuçta geçemiyorlar gibi dedim. Yoksa geçiyorlar o yüzden mi geçemiyorlar?
So let me answer this way. So basically, so what you're saying is true. So the values here can never go to the right of this value. Okay? So now if the primal problem is unbounded, then I can make C times X as large as I want, right? Okay? So by definition, remember the objective function actually goes to plus infinity. Okay? In a maximization problem, in an unbounded problem. So basically that means that if that is the case, I cannot find an upper bound on the optimal value. Okay? So if I cannot find an upper bound on the optimal value, then I cannot find a feasible solution for the dual problem. Exactly, exactly. Okay? So in other words, there is no value of the dual problem that will give me such a bound. There cannot be such a value. That's the point. Okay? So basically, if the dual problem had at least one feasible solution, then that would give me an upper bound on the primal value. Okay? So what I'm trying to say is that such a bound cannot exist, basically. Okay? So, but this implies that the primal objective function value cannot take larger values than W bar times B. So which means that, my objective function value is bounded above, basically, okay, for the primal problem. Well, if the objective function value is bounded above, then the objective function value cannot go to infinity, basically, okay? Okay, and if it cannot go to infinity, then the problem cannot be unbounded. Okay? So, but in this case, the primal objective function value cannot take arbitrarily large values. So this implies that then P cannot be unbounded. Okay? So, the main idea is the following. As soon as you find a feasible solution for the dual problem, you're automatically finding an upper bound on the primal optimal value. Okay? And as soon as there's an upper bound on the optimal value of the primal problem cannot be unbounded, basically. Okay? So we're just putting 2 and 2 together in some sense. So this gives us a contradiction. Therefore, the dual problem is infeasible. The dual problem has to be infeasible. So once again, the easiest way to think about this is the following. If I can make the primal objective function value as large as possible, then obviously I cannot find an upper bound on the optimal value of the primal problem, okay? And the upper bounds are given by the primal feasible solutions. So if there's no upper bound, then there's no, dual feasible solutions rather. If there's no upper bound on the primal value, then there cannot be any feasible solution for the dual problem. Okay, that's the idea. And the same is also true in the other direction as well. If this problem is unbounded, then this is to be infeasible. Okay? So what this says is the following. Whenever you have primal dual pair of LP problems, okay, if one of these two problems is unbounded, at least one of them is unbounded. For example, if the primal is unbounded, then the dual is infeasible. If the dual is unbounded, primal is infeasible. That's all it's saying right now.
Can they be both unbounded?
No, they cannot. So because if one is unbounded, the other one has to be infeasible, right? Okay? So as soon as one problem is unbounded, the corresponding dual is always infeasible. Okay? Other questions? So is that, argument clear? So think about the real line. Okay? So as soon as you have a feasible solution for the dual problem, that gives you an upper bound on the primal value, primal objective function value. Thank you. But if there's an upper bound on the primal value, then the primal problem cannot be unbounded. So then you cannot make C times X as large as possible. Okay? Because you're bounded above by this value. So in other words, if you can make this as large as possible, then you cannot find such an upper bound. And if you cannot find such an upper bound, then D cannot have a feasible solution. So that's the basic idea, basically, okay? And the same is true in the other direction as well, of course. Okay? If you have a primal feasible solution, then your problem cannot be unbounded. You cannot make W times B as small as possible because you're blocked below by the primal solution. Is that clear? All right. Let me give you an example. Infinite minimum.
paraleller çakı işaretleyip line üzerinde optimumlarımız varsa eğer ama hani bu olayla aynı nasıl oluyor?
So there's one thing you need to be careful about. So remember, even if you have multiple optimal solutions, then you still have a finite optimal value, right? The optimal value is not unbounded. So the problem being unbounded is different from having infinite many optimal solutions.
Yani hani onu anladım da hocam şey diye soruyorum yani tek bir optimum yerine işte infinite olduğu zaman.
So there's one thing you should be careful about. So if the problem is unbounded, remember there is no optimal solution, right? So if there's an optimal solution, then the problem cannot be unbounded. Okay? So in other words, if the problem has an optimal solution, then the optimal value is finite. Okay? So as a result, what you're saying cannot happen. Okay? Let me just give you an example. So let's consider the following example. Here's my primal problem. So I want to maximize x1 plus 2x2 subject to x1 is greater than or equal to 1 and x2 is less than or equal to 3. Okay, x1 and x2 are greater than or equal to 0. So let me just draw the feasible region. Again, I have two variables, x1 and x2. So the first constraint says that x1 is at least as large as 1. So it's everything on or to the right of this line. And the second one says that x2 is less than or equal to 3. So 3 is somewhere over here. So everything should be less than or equal to 3. So this is my feasible region, basically, right? Together with non-negativity constraints. Okay. So what does my isopropyl line look like? Well, so for example, let me look at x1 plus 2x2 equals 0. So it goes through 0, 0. And if x1 is equal to 1, x2 is equal to minus 1 over 2, which is somewhere over here. So it goes through these 2 points. Okay. And what's the improving direction? So it's given by 1 and 2, basically. Okay. And that vector looks like this one. And it's not too hard to see that the problem is unbounded, basically, right? Because I can push this line as much as I want, and I will never leave the feasible region. Okay. So as a result, the primal problem is unbounded. So by corollary number 2, it should be true that the dual problem should be infeasible. Okay. So let's compute the dual problem. Again, I have 2 constraints. I'm going to call W1, W2 the multipliers, the corresponding multipliers. So what does the dual problem look like? Let's start with the objective function. So I have W1 plus 3 times W2. That's the objective function. So minimize W1 plus 3W2. Subject to. Now what are the constraints? W1. Let's forget about the sign for now. What's the right-hand side value? 1. Okay. What about the second column? So I have W2, and the right-hand side value is 2. So now let's try to determine the correct signs, because we have different types of constraints. We should be careful for the final problem. Now, the corresponding primal variable is x1. Okay? And x1 is greater than or equal to 0. We have a minimization problem. If you look at the duality table, you're going to see that the correct sign will be greater than or equal to, basically. Okay? Similarly, you have x2 is the corresponding primal variable. And since x2 is non-negative, then the correct sign, once again, will be greater than or equal to. Okay? Next, I need to determine the sign restrictions for W1 and W2. So if I look at W1, the primal problem is a maximization problem, and the constraint is greater than or equal to constraint. Okay? So what's the sign of W1? It's going to be less than or equal to 0, basically, right? Because remember, we're trying to get an upper bound on the optimal value, so we have to reverse this inequality. To reverse this inequality, I need to multiply by a negative number, basically, okay? So as a result, W1 is less than or equal to 0. What about W2? Well, so this is already a less than or equal to constraint, so W2 should be non-negative, okay? So this is my dual problem. Okay. Now, why is this problem infeasible? Well, just look at these two restrictions. So W1 cannot be greater than 0. W1 is at least 1. Okay? And there's no way you can satisfy them at the same time, right? Okay? So what does this imply? Well, this implies that the dual problem is infeasible. So you can never have a value of W1 which is at least 1 and less than or equal to 0 at the same time, basically, okay? So as a result, the dual problem has to be infeasible. So which means that I can never find an upper bound on the optimal value of the primal problem. Okay? Is that clear? Okay, any questions? All right, so let's take a break. We'll continue.